I can't see, Anita doesn't seem to be connected. If you see her trying to connect, please let me know, okay? So, so I was talking about the general idea behind scattering. So you must remember this particular problem in optics, where we had an incident wave hitting a piece of glass. You know, so you had like a slab of some dielectric material, and we had the incident wave reflecting on the surface of this material. And some of this incident wave would be refracted inside the glass, right? Yeah. Then, normally what we do in undergrad, in the undergrad physics courses, is to just look at this interface. Now, of course, in optics, when you build an optical element, you usually think about a lens, you know, and you have an exit boundary also. And the same process occurs in the exit boundary condition. We have an incident wave that gets refracted or transmitted through the lens, and part of it is reflected internally. You know, so part of the incident wave is trapped, if you want, inside the lens. You know, there's an internal wave. Okay, so the net. I mean, when you look at it from a global point of view, you have an incident wave and then a reflected wave and then a transmitted wave. But what I'm trying to convey now is that in geometrical optics, we also had an internal wave inside the lens or inside the slab or whatever the electric we're looking at. Okay. So with this in mind, let's look now at the problem of scattering of an electromagnetic wave onto some particle. So this is the particle. This is a dielectric obstacle, in this case, of an arbitrary shape we see here. And so we can imagine that the interaction of the incident wave with the obstacle will lead to the scattered wave, which is like the transmitted wave, if you want, in case of the slab, but also includes the reflected wave. So the scattered wave is what we call the transmitted and the reflected wave. And of course, there'll also be something like the internal fields inside the obstacle. Okay, so that's important to bear in mind. We have the problem of scattering, we have the incident wave hitting an obstacle, leading to a scattered wave and internal fields. Okay, any questions so far? Good. I'll go on. So imagine now that we have a small obstacle. So let's consider a small obstacle whose total dimension is less than the wavelength of the incident radiation. Independently of this approximation, we can write the incident wave in terms of this monochromatic plane wave. Okay, and here it's important to bear in mind that well, we've assumed a harmonic time dependence. Okay, so this is multiplied by exponential I omega t. And another important thing to note is this unitary vector that describes the incident polarization. So we spent a lot of time, too much time perhaps, discussing this aspect. This particular vector is a way to write the polarization of the incident wave. Okay, so remember that in the case of complex E0, we could describe a circular polarized wave. Okay, so when the incident fields reach the target, they induce internal polarization and magnetic moments. So basically, they induced small electric dipoles. They separate the charges. The electric field pulls the positive and negative charges away. This induces electric dipoles. They generate currents, microscopic currents. And so this interaction is described exactly the same as in electrostatics, when the dimensions of the target are much less than the wavelength. If D, okay, so we saw this last time, if D is much less than lambda, okay, so here is our obstacle, any point inside the obstacle will be in the near zone, where all fields have the same time dependence. They are static fields. I mean, like in the sense static, in the sense the same fields as in electrostatics. Okay. And these, well, then, the complex problem of scattering and radiation boils down to electrostatics in the near zone when we have this case, right? When the object is much smaller than lambda. And so you can picture here that these fields will correspond to internal dipoles, magnetic and electric. And these dipoles will themselves induce radiation, right? I mean, we saw that last time, that when we had the electric dipoles or magnetic dipoles, we could generate electric dipole radiation or magnetic dipole radiation. Okay, and so these induced moments are going to be responsible for the scattered field. Okay, so this is what I'm trying to summarize here. The induced dipole can in turn generate electric and magnetic dipole radiation, resulting in the scattered terms. So this is what we're looking at now. So bear in mind the notation we have here. Okay, I'm labeling 2 everything that's outside the object. So let's remember and write the zone here. So zone 2 is outside, and zone 1 is inside. Okay, and so everything with a subscript 1 will be inside the target, and subscript 2 will refer to outside. Now, outside is 2 things. There's the scattered field and the incident field. Okay, it's both things, right? You can imagine here we have superposition of the scattered fields, which are emitted by the induced dipoles, plus the incident field. Okay. So this is like the context, okay? Now we'll try to work out these scattered fields. And it turns out that the problem is quite complex. Like, for instance, in the upper right corner here on my slide, we see this logo, which is an artist's impression of what is called Mie scattering, which is exactly the same problem as I've been describing to you, but for the case of a hard dielectric sphere. So we have a sphere here made of a dielectric material. You can imagine a sphere of glass, okay, or sand, particle. I mean, it's going to be spherical, okay? And here is a representation of a plane wave hitting the sphere, and the lobes you can see around it correspond to the scattered field. Okay, So of course, we see that there's lots of resonances and diffraction patterns, and there's a big frontal maximum here, forward scattering peak here. So this is again an artist representation of what Mie scattering looks like. Okay, so let's try and figure out the physics behind this. We have to introduce a convention here of the geometry. So this is the incident beam here, and that's the particle. Okay, and here we are labeling we are placing the Z direction, the Z axis, parallel to the incident beam. So incident beam is along the Z axis. Okay. And X and Y corresponded to the planes of the transverse incident waves. Now let's look at one particular direction in this centered on the particle. Okay, so let's look at this basis of vector here. And this is the radial unitary vector. Okay, that's the ER. Okay. And that is pointing toward a particular direction from the point of view of the obstacle. Okay, so if we look in this direction, we're looking at the fields scattered towards this direction ER. Okay. Now we can also introduce these parallel and perpendicular unit vectors. So this is a little bit hard to follow. Compared to the typical spherical coordinates, E parallel would be E theta. Now, I don't know if you can make out this is a theta, which is orthogonal to ER, right? That's theta here. And this other one is phi. So for standard spherical coordinates, E theta, E phi, and ER would be the normal way to call these spherical coordinates. Okay, this would be a set of basis vectors centered on this point at a distance r from the obstacle. Okay. However, for the problem of scattering, we won't be using exactly this set. We'll be using this one, which we'll call E parallel. This is the subscript S to mean this is scattering, okay? And the other one would be E perpendicular, which would be opposite to E phi, okay? So the idea here is simply that we have, we've used as a reference being parallel or perpendicular to what we'll be calling the scattering plane. Scattering plane would be the plane that includes ER and EZ. So the incident beam and the direction of reflection or scattering direction, ER, forms a plane. And this plane will be the scattering plane, okay? So what's important to remember here is that we have the scattering problem. An incident beam defines the vertical direction Z, and we're looking at one particular direction, an arbitrary direction, but let's focus on this one, ER. ER and EZ form a plane, which is called a scattering plane. And you were using this set of unit vectors to describe the polarization state of the emergent fields. So E parallel to the scattering plane and E perpendicular to the scattering plane. Okay. So in the outside region, zone 2, the fields then are superposition of the incident electric and magnetic fields and the scattered versions. Okay, that's what we've been saying. All right. As I anticipated, it's convenient to describe the polarization state of fields onto the scattering plane. Okay, so to do this, for instance, if we want to describe the polarization state of the incident radiation, we'll have to project the unitary vector representing the polarization of the incident wave onto the plane of scattering. Okay, And this leads to these two components, right? Parallel and perpendicular to the plane of scattering, okay? In this case, of course, ER is EZ because we're talking about the incident field. Okay, so I'm going back to the sketch now. We have this incident field here. Well, we have them here, E parallel and E perpendicular. Yes. So you have to imagine that E Z is also here, right? So the incident, the direction of propagation of the incident beam is towards the Z-axis, and so the incident wave is a transverse wave and lives projected into this plane, E perpendicular incident and E parallel incident. So if this is making you dizzy, it's normal. This is not easy. And you can easily get lost in the geometry of it, okay? But for now, just need you to just follow the basic idea, okay? There are homeworks for you to work on and look at carefully later on. So for now, just looking at the sketch, you can imagine that the incident electric field will live in the plane defined by E perpendicular incident and E parallel incident. Okay, I mean, this is a 3D render of rendering of a three-dimensional situation, and E parallel incident and E perpendicular incident are meant to be perpendicular to the incident beam. Okay, I'm not sure how obvious this is from the sketch, but this is the idea: is that this is E, the direction of the incident beam. Okay. Good. So this is the incident beam decomposed into this set of basic vectors, and likewise for the scattered electric field. Once we're far away from the target, the scattered field would be in the wave zone. So the waves would be transverse and spherical. It'll look like this. The amplitude of the scattered electric field will look like 1/r. And we decompose it into these unit vectors that represent this, defined in terms of the scattering plane. Okay. And as I anticipated, we have, well, E parallel is the same as E theta, and E perpendicular is just the opposite of E phi. Okay. And we have this relationship here. So they form a direct set of orthonormal vectors. Un triedro directo is what I meant to say. Now comes a bit of, so this was just the geometry of it. We'll now try to connect with the physics, okay? So the Maxwell equations are linear. It means that if I place an incident field, suppose that imagine that I'm hitting. Let me see. Let me draw this perhaps best. Okay, so imagine that we have a linear polarized electric field hitting an obstacle. Okay, this is a very ugly obstacle. That's a better one. And that leads to, so that would be scattering angle. And we are looking at fields here. Okay, so this would be the scattered field. Okay. Scattered field is going to be transverse too, so it must be like in this direction, yeah. And now suppose that we have another incident field. So we have, this would be one, and we have another one. Let's write down like this, coming towards us. This is another incident field, and will also be deflected in, well, we're looking at deflection in this angle here, theta, and so that's going to correspond to some other scattered field. Okay. If we sum, let's call these ones E prime and E second. So that would be prime and second scattered. What I'm trying to say by linearity is that the total electric field, E prime plus E second incident, will correspond to a scattered field, which is simply the sum of each of the individual scattered components. Okay. So this is what we mean by linearity here. So we can imagine then that the scattered fields are going to be linear combinations of the incident fields. It is apparently a horribly complex problem in the sense that the details of the interaction with the obstacle are difficult, and they depend on the shape and composition of the obstacle. But all in all, it's just a linear problem. Okay, so that's important to realize, and we see that we can write the scattered fields this way. So we have the transverse component. By convention, we've placed in here a minus I in the denominator. This is just a constant number, so it could be absorbed into the linear combination. But it's important here to highlight the spherical wave embodied in this term here, which represents the far zone. We're looking at the far zone. Bear in mind, we're not looking at the complex of the complex details of the intermediate zone. So in the far zone, we just have a transverse spherical wave, and the emergent scattered fields depend on what you throw at the obstacle. Okay, so and we've just seen that this dependence is linear. So one way to read this is to write down the components of the scattered field. So that would be the parallel and perpendicular components. So meaning this, what I've drawn here is both the perpendicular components. Okay, parallel component would be, for instance, in the case of this particular one, would be this one. That would be E second S parallel, and that would be perpendicular. Okay, so this matrix here embodies the details of the interaction. Okay, so this is not easy to absorb and digest, but it's in the end quite simple. We're just remembering that the Maxwell equations are linear, and therefore the emergent fields are going to be linear combinations of the incident fields. The details of the interactions are embodied in this scattering matrix. So this is called the amplitude scattering matrix because it refers to the electric field. We'll now see the full scattering matrix, but it's important to understand the origin of this idea of the scattering matrix. It's the linearity of the Maxwell equations. And we first look at the amplitude scattering matrix, which relates the incident and emergent electric fields. Now, you must bear in mind that there is an angular dependence here. This is okay, but it depends on the direction of scattering. It depends on this angle theta, okay? And if this obstacle is got a complex shape, you also need to specify phi, the direction of theta and phi. It's only in this direction. The scattering amplitude depends on the direction. okay? So what's interesting for us is the Poynting vector, okay? So in the region 2, which is outside the target, okay, the time average Poynting vector is going to be given by this relationship, right? So this is the real part of E cross H outside the target, okay? And the electric fields and the magnetic fields outside the target are composed of the sum of the incident and scattered waves, okay? So when you take the cross product here and you take the real part, it turns out that, well, this is easy to work out, that you can write down the Poynting vector in terms of these 3 components. So the first one you recognize is the incident Poynting flux. Okay, so when you take the Poynting vector anywhere outside your target, you'll recover the incident radiation field. You also have the scattered field, which is ES cross E, this one, responsible for the scattered fields only, okay? And there is the cross terms. So these cross terms are labeled X here, because we'll see that these cross terms, the ones that couple the incident and the scattered fields, are the ones responsible for the extinction of the radiation. Okay, so this is not at all obvious. It's not at all easy to anticipate, but it turns out this is the case. So we'll see why shortly. Okay, so summary: the Poynting vector outside the target in region 2 can be decomposed in terms of the incident Poynting vector, the scattered Poynting vector, and this crosstalk term, this the terms where we have the cross products between the incident and the scattered fields. Okay, so this is literally a crosstalk between the incident and scattered fields. In our, yeah. So this is like, or if you want, the interference between the incident and scattered fields. Okay, but it just comes out of this formula when you work it out, you know, and it turns out you can easily identify the incident and scattered fields, and you have this extra term which have got mixed terms. Okay, and we call it Ext because it causes extinction. So the Stokes parameters so the Stokes parameters are defined exactly the same as we saw a couple of chapters ago. We have IQUV, except that we're not using the same notation here. We're using the notation that refers to the scattering plane. We're using, because we're decomposing the electric and because we're decomposing the fields in these new bases, E perpendicular, which would be, well, for instance, this purple vector here, and E, so that would be E parallel, and that would be E perpendicular, okay? So you're using these vectors to decompose the electric fields. And so this would be the way to write down the Stokes parameters, okay, in the case of the scattered fields. Now, you can imagine that we want to connect these scattered Stokes parameters with the incident Stokes parameters, okay? So let's look at one, for instance. Let's look at, yeah, let's look at Q, okay? So QS is E perpendicular S. Well, it depends on these combinations, okay? Good. And so let's take one, for instance. Let's take E perpendicular S, this one, okay? We go back to the definition and we have it here. So this is, of course, a set of two linear equations, okay? And you look at E perpendicular S, and that's going to depend on S4 E1 and S1 E perpendicular I, okay? So you can write down these two equations and connect E parallel and perpendicular S with the incident field. And when you do this, so we were looking at this, you can plug this in here, and you'll be able to write down QS in terms of the incident fields, and then identify the Pauling parameters in the incident field. So it is quite tedious, and that is why I'm only suggesting you do the calculation for selected terms. You don't do them all. Just pick these ones. Try to reproduce this particular few. In this way, you have a clear idea of how this works. Okay. So it's quite important to do this because the topic is quite advanced and complex, and yes, we need it to describe the interaction of radiation with particles, which is daily life in astrophysics. Okay, so you need to understand the scattering matrix, and this is the scattering matrix, the S matrix. So when you do radiative transfer, if you want to do it exactly, using maybe a numerical package, but you need to describe the scattering using the scattering matrix. So this is the full-blown calculation, and I think it's important to have an idea of what goes on behind it once in your life, at least. So about the extinction term. So we are considering then a sphere centered on the target particle here, and that sphere is labeled A. It's a surface A. Okay. You can imagine that we can compute the flux over the total Poynting vector through the sphere. So we have some Poynting field, some field for the Poynting vector everywhere in space. Okay, and we can compute the flux of the Poynting vector through the sphere A. So since the flux of the incident field through this sphere is going to be 0, you can imagine that everything that comes in is going to come out for the incident field. And so the flux of the incident field through the sphere A is 0. Okay. So that part is not going to contribute. So, I mean, you have to bear in mind. Let me write it down here so you remember this. So S2 is the sum of maybe E2 is the sum of E incident plus E scattered. And so that led to a Poynting vector, which was the sum of the incident, scattered one, and the cross term. Okay, so since the flux of the incident field through the sphere is going to be 0, whatever comes out of the flux of S2 through the sphere is going to belong to the scattering effects. Okay, so whatever radiation is absorbed by the particle or emitted by the particle, but whatever is lost or gained in the interaction. Okay. So this is what I've just summarized. Equation 9 is where this comes from. Okay. We write the flux of the total Poynting vector, which is labeled S2 here, is only labeled S in my slide. And the flux through A, with lower caps A here is the same as this means the sphere. So this is the flux through the sphere. Can be written thus. Okay, so the ER is parallel to radius, so perpendicular to the surface of the sphere. Okay. And we write it, we decompose S in terms of SI, SS, and X extinction to write down the flux of the incident Poynting vector WI, which is minus the surface integral of SI. And we have chosen to define WS with a minus here. And this time we have a plus then in this definition of WS. And we have W extinction as expected. So as anticipated by symmetry, the flux of the incident Poynting vector would be 0, because I mean it's kind of obvious, everything that comes in through the sphere is going to come out for the Poynting vector, for the incident Poynting vector. And therefore, we see that the term, we have this relationship between the flux of the extinction term of the Poynting vector, so this term here, okay, is the sum of the total flux through the sphere plus that which has been scattered by the particle. Okay, so right, and we have a change of signs in W scattered. Okay, so we see that the extinction term is the sum of I call this the power absorbed by the particle WA, and that's scattered by radiation of the scattered field. Okay. So yeah, I missed a step in the reasoning here, so I need to rewind a little bit. This W small a is indeed the flux through the sphere, but I've labeled it lower caps A because it's also the flux absorbed by the particle. So how does that work? We have that WA would be, yes. If there was no particle, WA would be 0, is the way to see it. If there was no particle at all, then only there would be no scattered and then no crosstalk terms. There will be only SI, and W, the integral of the flux through the sphere would be 0. Okay. So it's when I'm at the particle that we have this loss of flux, or it depends on the sign you choose, okay? But the flux to the sphere is non-zero because of the particle. So that would be why we call it the absorbed term, that term which is that part of this is energy per unit time. And this is what we call the absorbed radiation, that's which is lost. If it's negative, then it's gained by the field. And we have finally this relationship between the flux of the crosstalk terms, the extinction terms, and the total flux or the absorbed flux, and corrected for that which is scattered. So of course, the component that's scattered is not lost. I mean, this the flux of the scattered fields is just the flux that are radiated away. Okay. I mean, it does make quite a lot of sense. I mean, we're saying that the total Poynting vector in the scattering problem is decomposed by the incident vector, whose flux through the sphere is 0. Okay, we know that. Then the scattered component, which is non-zero, it's got a flux which is non-zero through the sphere because this is radiating away. We know that this is going to go into the far zone, and we have radiation here. So this is positive flux going through the surface, you know, and whatever is not adding up. All that's lost, if you want, is this cross term. Okay, so I'm going to repeat this. It's not so easy to follow, and maybe not so easy to explain either. Look at equation 23 here. The total flux from the sphere, okay, is going to be the flux of the incident radiation corrected for the flux of the emergent scattered fields, which are radiating away. So and we know that this is going to contribute a positive component through the sphere. It's radiating away, and it turns out that we have also this additional term, okay? And this additional term is not being radiated away. It's because what's radiated away is this scattered, are the scattered fields. This is like a cross dot term. You know, if we are very far away from the particle, then all that remains is just these scattered fields, and this is what is being radiated away. You know, but that's not necessarily equals to the total flux through the sphere, which would be the difference between that which is this extinction term and the scattered terms. So do you see why this is so important and sensitive? We see that we can easily picture the flux of the scattered component through the sphere, okay? And that's non-zero. We see also the flux of the incident fields, and that's zero, you know? But when you compute the total flux of the total Poynting vector through the sphere, it's not WS. There is this additional term, W extinction, okay? And that is going to be the term that is absorbed or removed from the fields. Okay. To focus, we have a linearly polarized wave in this example, just to make a concrete example here. So we can write the incident field this way, where we have EI is parallel to, so this is a transverse wave, and is traveling in the Z direction, and the incident field is only linearly polarized in the X direction. So the scattered field is going to be a linear combination of these incident components, where S is the vector scattering amplitude. You can compute this from the scattering amplitude, plugging in the corresponding theta and phi. This would be a straightforward geometry. We won't work it out here, but you can imagine, I guess, that you can write down. Yes, I mean, if you're given the scattering amplitude, then you can compute one particular ES as a function of this particular component polarization state. And this is the scattering amplitude, right? The amplitude scattering matrix, S2, S3, S4, S1. And so we can compute, well, this is a bit tedious. I'm giving you this as homework, so you have a clear idea where it comes from. But it's worked out in this textbook. So the homework is just look at this textbook. I need to share with you this book, Bohr and Hoffman, which is where I'm taking this material from. It's not from Jackson. It's not in the textbook either. It's a book devoted to Mie theory. you compute the flux of this of the crosstalk terms E scattered, E incident through a sphere whose radius r is much greater than lambda, and you can reach the conclusion that the extinction term is dependent on just the forward component of scattering. So this is a little bit. It's also called what is it? I mentioned it later on. I forgot the name. It's a theorem. This extinction flux. So I remind you, this is the flux of this term S extinction, which is the crosstalk between the incident and scattered fields. And these this is the projection of the scattered component, scattered field embodied in this vector scattering amplitude against the incident plane of polarization, and you evaluate this in the direction in the direction of forward scattering. So it would be towards the big lobe here, towards the Z direction. So the total flux of the extinction component depends only on the scattering amplitude in the forward direction. So this is called the theorem of central optical theorem. The optical theorem. That's what it's called, the optical theorem. But never mind the vocabulary now. The point is that we introduce the extinction cross-section, which are exactly the same way as we defined it in chapter 1. And so following equation 24, which is this one, where we have that the extinction term is WA plus the scattered and the absorbed components. So this rings a bell, I guess. So this is the total extinction cross-section is due to the absorbed component and the scattered components. Maybe I should have started with this. It's easier to picture it in this way. Equation 25 and 26. Okay, so this is where we relate the scattered and the incident fields. Give you that the scattering cross-section is given by this angular integral, we can identify here this differential scattering cross-section, which would be just what's in the integral here. So this is a way to calculate the scattering phase function. If you're a little bit lost and well, it's normal, this is super difficult topic. You need to go slowly through it and look at the reference textbook, Bohr and Huffman, to understand, where does this scattering phase function come from. Because of the again the linearity right, yeah. So because of the linearity of the Maxwell equations, if the obstacles are randomly distributed, there's no interference phenomena between them, and we can expand on this later on. Then the phase function will only depend on the scattering angle theta. Since even if the obstacles are not spheres, or as long as they're randomly oriented, on average, the phase function will only depend on theta. So this is what I'm trying to say here. We have this incident field and that would be the assembly of particles which are variable shapes. So I'm placing whatever shape. The point here is that they're well mixed. And it's a homogeneous average. And if it's a homogeneous average, on average, there is no preferential direction. And so all that matters for scattering is this angle, theta. So that would be EZ, that would be ER. This angle theta is all that matters for scattering if this is a homogeneous mix, or if they're all spheres. And you can also define the asymmetry parameter, which is a way to estimate how asymmetrical is the phase function. So here is a representation of the squared phase function for me scattering on a hard sphere. And you can see that in this representation, this is very forward scattering. Okay, so there's a big forward lobe. So that would mean that G is very close to 1. Normally, we report the cross sections in terms of this Q parameter, which is exactly the same as the extinction coefficients, which is composed of the scattering and absorption terms, but they are normalized to the cross section of a sphere with a radius A. Okay, so it would be the cross section seen by the incident radiation if the obstacles are just spheres. The above results were computed only for the X polarized incident light, but they are easily extended to Y polarized light. And if you have natural incident radiation, so without non-polarized light, then the net extinction is given by this formula. We can also introduce this another connection with chapter 1, which was the extinction coefficient. This is correctly the extinction coefficient. This is the extinction cross section, and it's related then by the number of obstacles in a given unit volume. Okay, I know that today is going to be. It was a little bit. Oh, Nitya, you managed to join. I just saw you now. You are outside the gallery. So I know that this was a little bit difficult to follow today. I'll try to briefly summarize for Thursday, which will be our last lecture. Okay. Good then. I'll try to upload this, and if you have any questions, please let me know. My aim is to finish the course with this chapter. Okay, so this is what we saw. Basically, we finished the course here after scattering and diffraction. This chapter on relativity and relativistic phenomena, I'm sorry, you'll have to look at it on your own. And radiative transitions too. Simply we don't have time. Okay, but I mean, we can't do everything, and it also depends on your specialty. Not everyone is interested into synchrotrons, constant scatterings, and and conversely, not everyone is interested in radiative transitions due to atoms or molecules. So, I mean, if later on you need these material for some research work or coursework, or if during the rest of your studies you need this material, just let me know, and I can help you out if you have any questions about those. Let's try and wrap up the course at the end of chapter 4 here, scattering and diffraction, and see if we can manage it all. Okay, there's quite a few homeworks in this chapter, and I hope that these homeworks will be useful to you to try and absorb the material. Good, thanks very much for attending today, and see you Thursday then. Ciao.
Ciao.